Welcome to Unit 5 of Calculus and Vectors, Curve Sketching and Optimization. They're two very important branches of calculus for different reasons. Optimization is all about trying to take a situation and finding the optimal value, the best value. So it's a very practical sort of skill to have. Curve sketching, well, maybe not as useful in the general sense. It's very telling and very interesting because it kind of reveals to us how much information we can gather about a function using calculus. And in fact, if you go into computer science, if you are making graphing software, or you have to, or even like uh, graphics editing software, there's a lot of applications that have to do with analyzing shapes and using formulas. So there's a fair bit of calculus in that as well. I'll kind of skip over this first section, but I encourage you to have a read. But most importantly, in this lesson, we're going to talk about when we have a function, how to tell what's increasing and decreasing. So just in general, we're talking about a function. I'm just going to draw a little function here, maybe a nice cubic function. You notice that we have some intervals of increase and decrease. So basically, the big principle here, let's split up into some categories. So the first section of this is increasing, and you notice the slopes of the tangents are all positive, like this. On the second region, it's decreasing. And if we draw a tangent to the curve, it's going to be negative. And lastly, when we have the third section, it's increasing again, and the slopes of the tangents are going to be positive. So a few big takeaways that hopefully you'll get from that. Number one is that when it's increasing, the slope is positive. When the curve is decreasing, it's negative when the values are decreasing from left to right. So that's the first big thing. And we know that the slope of the tangent is connected to the derivative. So as it turns out, if the derivative is greater than 0 over a region, it's increasing. And if that's less than 0, it means it's decreasing. That's the first big takeaway. The next big takeaway is that we have those dividing lines, and you notice they happen whenever we have a minimum or maximum point on our function, whenever it changes. And you're also going to notice that those points, the slope of the tangent is 0. So as it turns out, with any sort of polynomial function, we're always going to have that change because we know with polynomial functions they're always going to be a polynomial as well. Maybe it's something like, maybe the derivative is something like, something like this. But we know that even there, we have to, if we want to go from positive to negative or negative to positive, we have to pass through 0. So for polynomial functions, when we have a derivative that's equal to 0, that's going to indicate a point where we're changing from either positive to negative or negative to positive, or maybe not, but if we do change, it has to be at a spot where f prime of x is equal to 0. So that's the trick. So the first thing we're always going to do is we're always going to take the first derivative of the function. We're going to set that derivative equal to 0. We're going to find out what points we're going to solve for x. So we're going to find those points where we have that maximum or minimum, because that's where we change from increasing to decreasing or decreasing to increasing. And we call those critical numbers. Critical numbers are the points where we switch from increasing to decreasing or decreasing to increasing. Usually, not always, but those are going to give us a good read of where those changes are happening. So from there, we can create intervals. So sections of the graph where we know everything is always increasing or always decreasing. So to help us with that, let's try that with a function. So example 1 says determine the intervals of increase and decrease for f of x equals negative x squared plus 4x. So first step, we said we're going to find the first derivative. So f prime of x is going to be equal to negative x squared becomes negative 2x, and then 4x becomes plus 4. Step 2, we said we're going to set that equal to 0. So 0 equals negative 2x plus 4. And then we just rearrange 2x equals 4, or we get x equals 2. So that's going to be our critical number. And we actually have that filled in up top. Usually we won't be given that table and we have to kind of figure that out for ourselves. But we're going to say that's that dividing line. So we know that to the left of 2, everything's going to be increasing or decreasing. And to the right of 2, everything's going to be either increasing or decreasing, but it's going to be consistent along that line because we know that that's the point where we have our derivative that's equal to 0. So now what we're going to do is we're going to try and figure out what's going on either side of that. So what we're going to do is we're going to look at our derivative, negative 2x plus 4. And we're going to factor it just to help us out a bit. Let's say that's negative 2 times x plus 2. So what we're going to do is, once we have a factor, we're going to examine all the factors and see what's going on. So for our derivative, by the way, we're just breaking down f prime of x here. This is going to be negative 2 times x plus 2. Now, negative 2 is always going to be negative. And that should be x minus 2. Let's fix that. So x minus 2, for something less than negative 2, we can pick any value of x. We could do x equals 0 would be a good example. So 0 minus 2 is going to be negative 2. So that's going to be a negative. And what I will tell you is that it doesn't matter what value you pick, as long as it's 1 in that region, that's going to work for us. So for x is greater than 2, pick some value greater than 2. Let's say 3. 3 minus 2 is 1, so everything in that region is going to be positive. So now we're just going to multiply our signs together and see what happens. So for x is less than 2, negative times a negative becomes a positive. For x is greater than 2, a negative times a positive becomes a negative. So what that means is, for the first part of this graph, the positive part, we said if the derivative is positive, it means we're going to be increasing. And for the other side, we're going to be decreasing. So actually, we've gained a whole bunch of information. We know that for this quadratic, the axis of symmetry is around x equals 2. And now we need to know what the vertex is, and we can start graphing this. So we just find f of 2, which is negative 2 squared plus 4 times 2, which is negative 4 plus 8, or that's 4. So we have a vertex at 2, 4. And so we can graph that, and we know that it's increasing going to the left of it, so something like this, and we're decreasing to the other side. Now, mind you, you're probably saying to yourself, for a quadratic, that's kind of simple. We already know how to graph quadratics based on an equation. But as we get more complicated equations, when we get polynomials, when we get other types of equations that maybe we don't know how to work with, these skills are going to become more and more valuable to us. We can actually learn a lot about a curve based off of the derivative. So let's try a different one. Let's try one that's maybe a little more difficult to figure out. So we're going to find the intervals of increase and decrease for f of x equals x cubed plus 3x squared minus 2. So first step, we said we're going to find the derivative. F prime of x is going to be equal to, the derivative is x cubed becomes 3x squared. 3x squared becomes, move the 2 up front, 3 times 2 is 6 times x, and minus 2 goes away. or we could factor that and it would be 3x times x plus 2. So next step, now we're going to set it equal to 0, and we're going to try and solve for x. So now we know with the zero product rule, we can say 0 is equal to 3x, 0 is equal to x plus 2, so 0 is equal to x, or negative 2 is equal to x. So we know that we're going to have changes to our increase and decrease potentially around negative 2 and 0. And so to deal with that, we've set up 3 regions. We're going to have everything to the left of negative 2, everything between negative 2 and 0, and then everything to the right of 0, which we've outlined over here. So now that we have that, let's take a look at those factors in the derivative and let's see what our signs look like. So take all the factors for f prime of x. So we have 3x and we have x plus 2, and we're going to examine them over each region. So for the leftmost region, everything to the left of negative 2, let's pick a number to test it. Say negative 3. 3 times negative 3 is going to be negative 9. And negative 3 plus 2 is going to be negative 1, so that's going to be negative. For the second region, between negative 2 and 0, let's pick another number. Negative 1 would work. 3 times negative 1 is negative 3. And then negative 1 plus 2 is positive 1. So on and so forth. Pick another number greater than 0. Let's pick 1, which is going to give us a positive and a positive. So for this one, we know that it's going to be the first region, negative times negative is a positive. We're going to have a positive derivative for the first region, then a negative for the second region, and a positive for the third region. So, and we said that if the derivative, if the slopes of the tangents are positive, then we're going to increase. If it's negative, we're going to decrease. And so for the third region, we're going to increase again. So now that we have that, now we know where we're increasing and decreasing. Now we just need to know our maximum and minimum points. We're just going to take f of 0 and f of negative 2, plug them into the original equation, and we get negative 2 and positive 2. So from there, now we're just going to plot those points. F of negative 2 equals positive 2, and f of 0 equals negative 2. And we said we're going to start to the left of x equals negative 2 by increasing. And then we're going to decrease. And then we're going to increase again. I'm going to draw that a little bit better because I think I can do a better job with that. Hopefully with your pencil and paper, it'll be a bit easier, but something like that. So now we've used that to plot a cubic function, which would be a little bit more difficult. We don't really have that many tools for that. So now it opens up a bit more opportunity for us. In fact, we can use it for any type of polynomial function. We can use this information to help us. So let's try a different type of problem now. So example 3, the temperature of a person with a certain strain of flu can be approximated by the function T of D is equal to negative 5/18 d squared plus 15 over 9 times d plus 37, where 0 is less than d is less than 6. T represents the person's temperature in Celsius, and d is the number of days after the person first shows symptoms. So essentially, we're examining the curve of the temperature of this person between 0 and 6 days. So question A asks, during what interval will the person's temperature be increasing? And question B asks, what is the maximum temperature during this interval? So let's start with question A. So it's essentially asking, what are our intervals of increase and decrease? So that same strategy we can use in this case. So we're going to find the derivative, t prime of d, to start. So that's going to be negative 5 over 18 times 2 is negative 10 over 18. So actually, I'll show a few of the steps just to help out a bit. So we're going to take the interval of the first term, which is negative 5/18 times 2 times d. And then the second term, it's going to be, that's a linear, so it's going to be just 15 over 9, just the coefficient. And then the constant's going to go away. It's going to be negative 10 over 18 times d plus 15 over 9. And we can factor that. That's going to be, we can pull out negative 5/9. And that's going to work out to be d minus 3. So now that we have the derivative, we said the next step is to set it equal to 0 and try and solve. In this case, the coefficient goes away. We're left with 0 equals d minus 3, or d equals 3. So that means that that's going to be the dividing line. To the left of 3 days, we're going to have either increasing temperatures or decreasing temperatures. And to the right, we're going to have everything increasing or everything decreasing. It makes sense that the person's temperature would be increasing to the left and decreasing to the right, but let's just do a quick table just to make sure. So I'm going to set up our table here. We said the first region is going to be between 0 and 3. Our second region is going to be between everything to the right of 3, between 3 and 6 days. So let's look at the factors for the derivative. Negative 5/9, and we have d minus 3. So negative 5/9 is always going to be negative. The day is not going to change that. All right. So for between 0 and 3, let's look at d minus 3. So everything there, doesn't matter what we pick for d, it's going to be negative. And then once we get past 3 days, it's going to be positive. So for the first part, negative times negative is a positive, so that's going to be increasing. And for the second part, negative times positive is going to be negative, which means it's going to be decreasing. So now we've definitively shown where it's increasing and decreasing. So first, last thing we like to do is summarize what they're asking for. It's asking when it's increasing. So therefore, the person's temperature increases between 0 to 3 days. And then the second question is asking, what is the maximum temperature? For that, all we're going to do is we're going to use our temperature function. We want to find the temperature after 3 days. So we're just going to take the original function, which is this one up here, not the derivative, because that doesn't tell us the temperature. It tells us how quickly the temperature is changing. So make sure you don't use the wrong function here. So we're going to use t of 3, which is negative 5 over 18 d squared, in this case 3 squared, plus 15 over 9 times 3 plus 37. Punch that into your calculator and you should get 39.5 degrees Celsius. So therefore, the maximum temperature is 39.5 degrees Celsius. So now we've gone through and we've figured out the maximum temperature using calculus. So one more type of problem that we might see here with these. It's going to ask us to sketch some functions. So it's going to give us some information about our function, and we're going to try to interpret it to help us figure out what's going on and what this function is going to look like. So for the first function, it gives us a few pieces of information. The first part says f prime of x is greater than 0 when x is less than 0. Then f prime of x is less than 0 when x is greater than 0. Then it says f of 0 is equal to 4. So the third part is easy to plot. That's just coordinates for a point. So that turns into 0, 4. The first part of this says f prime of x is greater than 0. And then we said that f prime of x means the derivative is greater than 0. So the derivative is positive, which means that this is going to be increasing for x is less than 0, for all values x less than 0. So it means that for the first part of this, we're going to be increasing as we go left to right. And the second part of this says the derivative is less than 0. So it means that in that case, we're going to be decreasing. We decrease over the region x is greater than 0. So everything to the right of that point is going to be decreasing. Something like this. So as it turns out, the information that we have here represents a parabola. That's all you need to do there. And lastly, we're going to do one more of these. Let's take all the information we have and let's see what we can figure out. So first part says f prime of x is greater than 0 when x is less than -1 and also when x is greater than 2. That's our first piece of information. The second piece of information says f prime of x is less than 0 when -1 is less than x is greater than 2. And f of 0 is equal to 0. So again, same basic idea, looks a little different though. So the first thing you should notice is that f of 0 equals 0 just represents coordinates for a point, 0, 0. So you can plot that right away. For the first part, what that's saying is f prime of x is greater than 0 means that we're increasing over, it's mentioning two intervals here. So x is less than -1, which is everything to the left of -1, and x, and let's see, and then we have everything x is greater than 2. So everything to the right of 2. Now it doesn't give us any specific maximum minimum points here, so we can just pick whatever we want and anything works. So here's the first region, and then for the second region, we could pick maybe this one here. Just make sure that they're at the right x values on your graph. And then for that middle criteria, it says f prime of x is less than 0 in that region, and -1 is less than x is less than 2. So that means that we're decreasing over that region. So that means that it has to decrease and it has to pass through that 0, 0 point and then go down to our minimum. And now we've drawn this function. So it turns out that this information is indicating to us this is some sort of cubic function. So that's pretty much it. That's all you need to know for this. Just remember the big pieces of information. If you're looking for the intervals of increase and decrease for a function, take your derivative, set it equal to 0, and that's going to tell you where we change from positive to negative. From there, then you can analyze what's going on. Is your derivative positive, in which case we're increasing over that interval, or is it negative, in which case it's decreasing? So make sure you do the practice questions, and I'll see you in 5.2.